Good afternoon. We will today start a new topic. In the machine learning algorithms, we have done one algorithm, which is the linear regression. Today, what we'll be looking at is another type of supervised learning. So we have seen machine learning, there are two types, supervised and unsupervised. So there is a supervised learning and there is unsupervised learning. And in supervised learning, there is one is regression. Anybody remembers what is the second one? There is a supervised learning. It has got two main subcategories. One is the regression, which we have seen linear as well as polynomial.
Classification.
That's right, Poonam. So second is classification. So today's algorithm that what we are looking at is of classification type. Although the name here is logistic regression, and this regression is a misleading word. So although the name is logistic regression, we'll see why that regression word comes there. But it is a classifier. It is a classifying model. Anybody remembers what is the main distinct difference between data for regression analysis and rather labels for regression analysis and labels for classification problem?
In regression, labels are
continuous.
continuous. In regression, the labels are continuous.
In which case they are continuous?
Regression.
Right. They are continuous or right. And in classification? Classification, you have the distinct values. So like it is a spam mail or not spam mail, or it's a healthy machine or unhealthy machine. Yes, no, or you can have multiple types also, spam mail, professional mail, and so on. Okay, so we will be looking into classification problem, and today's algorithm deals with that. Now let's go further into just a little introduction to classification problems. So as just now we have said that classification problems, the labels are categorical or discrete values. So you can have multiple labels. So you can have a general classification problem in which the labels could be multiple in numbers. So you can have like, for example, if it is an email classification, then email could be a spam email, professional email, personal email, and so on. The type what we are discussing here is called as a binary classification problems. So as the name suggests, the binary classification problem has got only two labels. So it could be spam or not spam, as the examples are given here, or if it is a machine health problem, that is a healthy or not healthy. Or if it is a condition of the road, it is good or bad, and so on. So we will see that the binary classification algorithm, that is logistic regression, is one of them. These algorithms can still be used for multi-classification. So how to do that, we'll see at the end of the lecture. So having understood that we are going to deal with binary classification, let's understand what happens. Means the first question is a quiz. So let me give link of the quiz. This quiz form. So let's, I want you to think about how this algorithm should be. So that's why this quiz is there. Some time for setup. Okay. So the link for this form is given to you. So I think except those from electrical and civil department, others are familiar with this form. Okay, so the question is, can we use linear regression algorithm that we developed earlier for the classification problem, binary classification problem. So, for example, the data given here is it is a univariate problem. So you have got noise as the feature and health is the label. So that is a why. So health can is a binary label. So it can be healthy, that is 1, or it can be not healthy, that is 0. So for a given noise level of a machine, you have collected some samples. So these samples are not healthy and these samples are healthy. So something of that type is given to you. Now, can you use the linear regression that we studied previously? So linear regression, what it does, it fits in the given data, it will fit a line so as to minimize the error. So we have seen the least square cost function. So in which we are minimizing, we are fitting a straight line, which will be the deviation of each of the samples from that line will be minimal. So it will fit some line in this particular form. Now, can we use this particular hypothesis function? So this hypothesis function is for linear regression. So which is h of x equal to theta 0 plus theta 1 x. So can we use this hypothesis function, or in turn, can we use linear regression for doing classification? Just think about that and give me answer. I'll repeat the question. Those who have joined new or suddenly realize that there is a question that can we use linear regression function for a classification problem. So for a given noise level, you can predict the health. Of course, since it's a linear regression, you will get some output which is continuously varying. Can you use that output for predicting whether it is healthy or not healthy? Okay, so let's see what is the trend. Oh, that's great. 50-50. That's very good. Yeah, so somebody says thinks that it can be used and somebody thinks it cannot be used. So I want one of you to take the initiative to explain your stand. So any one of you can explain whether linear regression can it be used or it.
So I think it can't be used for binary classification because we require only two output and
Okay.
here we get a continuous output, like we get different outputs, more than two.
Okay. Can you? I agree with you that for this particular sample you will get value which is equal to zero point 0.8. For this particular sample you will get value which is 1.5, and for this sample you will get value which is 10. Here you will get value equal to -1. Here you will get minus zero point 0.8. So what Prasad says is that since these values are something which are not 0 or 1, so for binary classification we require 0 and 1. This hypothesis function doesn't give us 0 and 1, so we cannot use it. Anybody uh, think it can be used with some logic?
So we could use it if we have a like have it if we predict above a certain value, then we put it as 0 or 1, and below that it is the opposite.
Okay, so what Nathan says that you can decide some demarcation. So the logical demarcation will be zero point 0.5. So all values below zero point 0.5 are not healthy or 0, and all values above that they are healthy. Okay, so in turn, whatever answers most of you have given, so both, if it is your in your mind, the thinking is either it could be in the way Prasad explained that we require values between 0 and 1, and this hypothesis function doesn't give you, but Nathan has, so that is also true. That is why we are studying the specific new algorithm. And the other point which was given, that if you are very desperate and you want to use linear regression only for this particular problem, then you can use it by with some logic that below zero point 0.5 it is 0 and above zero point 0.5 it is 1. So in that case, if this is the demarcation point, then if there are some samples which are to the left of this, those will be misclassified, and there are some samples which are to the right of this, those will be misclassified in this particular case. So in general, the answer to this question is that we can use it, but that is with a pinch of salt, or rather a lot of salt. It is not very elegant way of handling the classification problem, and hence we need to have a hypothesis function which takes the values between 0 and 1. So here we are talking only binary. So that is why the hypothesis function should take the value between 0 and 1 for whatever features that we are supplying. For every sample, the value should be between 0 and 1. It, it could be, one would say that it should be discrete value, either 0 or 1. But even if it is between 0 and 1, that is also okay for us, because we can again use the same logic that it is above zero point 0.5. If the value of the hypothesis is between zero point 0.5 and 1, then it is 1, and below zero point 0.5 and below zero point 0.5 and 0 is 0. So the hypothesis function we need to choose. So next we'll discuss about the hypothesis function for classification. So the property that we need is that is h theta of x bar. So x bar is your feature vector. So it is x1, x2 up to whatever number of features you are having. So this should be something which takes values between 0 and 1. So there are a lot of functions which are available for doing this particular, which have the values between 0 and 1. A specific function which we use for the purpose of classification is called as a logistic function. Hence, part of the name of this algorithm comes from the name of function which is used, which has values between 0 and 1. So it's a logistic function. It is also called as a sigmoid function. So both are synonymous. So in this particular function, the h of theta x bar. Okay, we'll bring in the hypothesis function little later. So let's see the logistic function in its mathematical form. So the logistic function is g of any z is given as 1 plus 1 divided by e raised to minus z. So let's see the nature of this particular function. So let's plot this function. So this is z, and this is the g of z, the value of this particular function. Okay, so the z values is, this is z equal to 0, this is towards plus infinity, positive infinity, and this is towards negative infinity. So let's first see what is the value of this function at z equal to 0. So at this point, can somebody tell what is the value of g of z? It's not that difficult. I asked what is the value of this function at z equal to 0?
Half 1 by 2.
Half, 1 by 2. So it is equal to 0.5 at z equal to 0. And what happens if z is positive infinity? So at the far end, for the right hand side end, when z becomes, so you can see that when z becomes positive infinity, this particular term becomes 0. So you reach the value of 1. So at very large value, you get 1.0. So as z approaches infinity, this function also approaches 1. And what happens when z approaches minus infinity?
0.
So the denominator becomes 1 plus e to the power minus of minus infinity, that is 1 by infinity, that is 0. So when it is z value is negative, at that point it approaches the value of 0. So this particular function has the property that we require. So this function, if you plot, it will look like this. So it takes the values between 0 and 1. So it meets our need. Now, before we proceed into how to insert, now we need to incorporate this feature vector. So some feature vector and the model parameters we have to introduce. So before we do that, let's understand one more aspect of this hypothesis function. When we say that hypothesis function needs to be between 0 and 1, it reminds you or remind us of a particular concept, that is that of probability. So in the logistic regression classification, we use the hypothesis function, which is just now we talked about. So this particular function, it indicates the probability of your sample being value of 1. So I'll repeat once again. The hypothesis function, which is used in the logistic regression, it indicates the probability of the sample being equal to 1, the label of sample being equal to 1. So whatever means in a particular set, you will have some data. So for example, you will have the RPM of the machine, the decibel level of the machine, and then you have health of the machine, which is given as 100 something. Some RPM, 1000 RPM decibel level, let's say 70, then 2000 RPM decibel level, let's say 60 and something. So if you take a particular sample, if you supply these numbers, so this is your x1, this is your x2, first feature, second feature, and this is your label, which is y. So if you supply RPM as 2000 and decibel as 60 to this function, the function will return the value. Let's say it returns the value equal to 0.8. So 0.8 is the probability that this particular sample will be having the value equal to 1. So it's 80% probability that this sample belongs to class 1. And for example, and just another case would be if you get the value of 0.2, when you supply these numbers to your logistics function, if you get the answer 0.2, which means that the probability of this particular sample belonging to value 1 is 20%, which means it is 80% chances are there that this sample belongs to class 0. So the hypothesis function is to be used in this particular fashion. So hypothesis function is nothing but the probability of that sample. So for every sample, whatever value of hypothesis function we get, that is whatever prediction you get, that prediction is nothing but probability of that sample being 1, a value of 1. So that 1 could be spam, not spam. So that assignment you can do differently. But the interpretation of this logistic function is as follows. Now, what we require is we have to supply the value of z. So for the hypothesis function, we will require to include the x and the model parameters, that is theta, are to be included. So in linear regression, we have the logistic, the hypothesis function, which is given as theta 0 plus theta 1 x1 first feature plus theta 2 x2 and so on up to the last feature, and the last variable, or in the matrix form, the same thing we can write it as theta transpose x, where x is the feature vector and theta is the model parameter vector. So in the similar fashion, if you want to define the h theta x bar, so we need to have we said that we'll be using the logistic function. So you require e raised to minus z. So this z value should be in terms of so whatever is the z value, that should be something similar to some. So this parenthetic term or z term should be some function of theta and xi. So theta and xi. So there are multiple possibilities are possible. In this particular logistic regression, the function used is logistic, and the value of z which is used is the same term that we used in linear regression. So here we use the term which is theta transpose multiplied by x. So that is how the hypothesis function or the prediction function for the logistic regression is being used. So in the more expanded form, this would be e raised to minus theta 0 plus theta 1 x1 plus theta 2 x2 and so on. And since this particular function is a logistic function, and we are also using a form which is similar to that of the regression, that's why the name regression appears in the logistic regression. So this logistic regression uses the logistic function, whose other name is a sigmoid function, which we'll again encounter when we are studying neural networks. So there also we'll be using this same function. So this particular function is used here, and as a combination of model parameters and the features of the problem, we use the form of model parameters and features in the same way as that is used in linear regression. So that is why this particular method is called as a linear, is called as a logistic regression. Okay, so any questions till here? So we'll have one short quiz to just explain this, just check your understanding. Okay, so just give your answers. So the question is, in binary classification, what does the value of hypothesis function for a sample indicates? Okay. Okay, so the correct answer is the answer 1. So here we are, I intentionally did not use the word probability here. Otherwise it could have used, you could have directly linked to the discussion there. So hypothesis function in logistic regression is a probability of the sample belonging to one class, or the class whose value is equal to 1. So that is the answer. So instead of probability, I'll use the word probability. It has nothing to do with the importance of the sample among all the samples. So it doesn't sort of says anything about the quality of the particular sample. It just predicts whether that sample belongs to class 1 or class 2. So in that sense, this particular thing is wrong, and then obviously the third one is wrong because of that. Okay, so now let's proceed. Now, before we proceed into the next thing is how do we determine the model parameters, that is theta 0, theta 1, and so on. So before we go into that particular part, let's understand the meaning of that term which comes in place of z, that is e to power minus theta transpose x. So what does that theta transpose x physically means? It has got some interesting understanding. So let's consider that the nature of this logistic function. So we have seen the logistic function. It uh, is exponential. So this is your h theta x, and this is your z, that is theta transpose into x, and the values are between 1.5 and 0, and this happens to be z equal to 0, and the function is in this particular fashion. Now we said that in order to determine the value of a particular sample or label, or in order to predict the label of a sample, we will use the hypothesis function as a probability function. So if the probability is above 0.5, we will classify that particular sample as belonging to one class. So here it is more than 0.5. So in this region, we will classify, so all these theta transpose x values above 0.5, or the g of that particular value. So we'll call them as y equal to 1. And the other part, we will classify them as second level, y equal to 0. So if the function value is below 0.5, it is 0, above 0.5, it is 1. So 0.5 is something which is where you cannot decide. So below 0.5, there is one class begins. Above 0.5, the another class begins. So this particular point where the probability or the hypothesis function value is 0.5 corresponds to value z equal to 0. So z equal to 0, which means that theta transpose x at that particular point would be equal to 0. So I will just expand this. So this will be theta 0 plus theta 1 x1 plus theta 2 x2 plus and so on. And that we are equating to 0. For the case of simplicity, let's consider only two variable problem. So in that case, we will have, just for the understanding, I'm just making it simpler so that we are considering a problem where there are two features, x1 and x2. So let's give some names. So let's say x1 is the RPM and x2 is the decibel level or the noise level of the sample. There are some samples which are unhealthy. So for low RPM, low decibel, so these are healthy problems, healthy samples. And there are some samples which are having high noise level. So these are unhealthy samples. So these samples y is equal to 1. For these samples, y is equal to 0. So any point which is lying in this particular zone, so this is x1, this is x2. So this particular problem would be healthy, or whatever class. This is y equal to 0 class, and this is y equal to 1 class. So 0 is a healthy class and 1 is unhealthy class. So if we define that way, then and you build your hypothesis function, and hypothesis function. So you know the values of theta 0, theta 1, and theta 2. And we know that at this particular, when this particular condition is satisfied, that is whenever theta transpose x is equal to 0, which is again this equal to 0, this corresponds to the value of hypothesis function h theta x will be equal to 0.5. So 0.5 means probability of this sample being class 1 is 50%. So it is sort of boundary or threshold below which or above which the class changes. Now, can somebody tell what is this form of equation? So in two-dimensional field, what does this line, this particular function represent? So theta 0, theta 1, theta 2 are determined, so they are constants. So what is this particular function in this? If you have to plot it on this particular graph, how it will look? It will be a line or curve, or what it will be? Circle, parabola, what is it?
Plane.
Okay, so this is two-dimensional. So plane is, if you are considering higher order terms, so this is just two dimensions, x2 and x1. So if you call this y and this as x, so this is nothing but theta 0 plus theta 1x plus theta 2y equal to 0. So it is y equal to mx plus c. So it's the equation of straight line. In higher, if you are more than two number of features, then what Poonam said is correct. Then it is the equation of a plane. So in this case, this particular um, condition getting satisfied represents a line, and that line has got a property where the probability of the hypothesis function has a value equal to 0.5. So which means that any sample which is lying, any point which is lying on this line has got probability of being type 1 as 50% or 0.5. So it sorts of, that is why it is called as a decision boundary. So this particular set of data points, one point set of data lies on one side, that is y equal to 0, and another set of data points lie on the other side of this particular line. And this is called as a decision boundary for the classification problem. So for logistic regression, since we are using this function is always a linear function, so the decision boundary will also be a linear. So in case you have a problem, like we will see an example next. So if you have some set of values where the linear boundary may not be appropriate, so there will be some classification problems where certain samples belongs to the way they are distributed as follows. So we would expect to have a decision boundary which is curved one. So require a nonlinear decision boundary. So using the logistic regression, which uses the hypothesis function as 1 divided by 1 plus e to the power minus, so let me write it, theta 0 plus theta 1 x1 plus theta 2 x2 and so on. So this particular trick we already have seen in polynomial regression in the earlier case. So in this case, this function is a linear function, but using this linear function with some trick, we can still model the nonlinear decision boundary. So can anybody tell how do we do that? If you remember how do we do that in polynomial regression, you will remember it. So in this case, we have two features, x1 and x2 are the two features. So 1000 RPM, 60 decibels, and your label, which is healthy or not healthy, 1200, 50, and 0, and so on. So if you use the the way we define the hypothesis function, you can have only a straight line classifier, so which may misclassify some of the samples. So you want to introduce the, you want to still use the same logistic function, but we want to handle this kind of problem which has got a nonlinear decision boundary. So how do we do that? So this equation is nothing but theta transpose x equal to 0. Anybody recollects how do we handle this particular case?
So take x1 as x1 square and x2 as x2 square.
That's right. So we introduce additional features. So in order to, yeah, thanks, Prasad. So in order to handle this particular, suppose you go ahead to solve this particular case with logistic regression, and you find that your decision boundary will be always straight line, but it doesn't uh, satisfy you. So you want to make this decision boundary as curved one or polynomial one. Then what you do is you simply expand your problem by adding some new features, artificial new features. So one is x1 square, which you called as x3, x2 square. It need not be, square is just an example. It could be x1 into x2 or something like that. So add artificial features into this particular problem. So your problem, instead of a two variable problem or two feature problem, it becomes four feature problem. And then you supply this data. That means here it will be 1000 square, here it will be 60 square. And then you supply this as a feature vector, x bar vector, and this as the actual value of the function. And with that, so it essentially means that you are fitting a function which is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 into x3, where x3 is x1 square. So it will be theta 3 into x1 square plus theta 4 into x2 square. So you are able to handle this particular problem, means you are able to fit. Now you will be able to get the decision boundary which is non-linear. Of course, at the cost of you are adding your computational resources, computational requirements you are increasing. By adding more features, you obviously are increasing the computational requirements. But that is what obviously, if you use some other function, then again it will have similar computational requirements. Okay, so we have seen till now, that is what is the hypothesis function in logistic function, and what is the physical meaning of that theta transpose x term which appears in the logistic function. So that theta transpose x is nothing but the decision boundary, or the boundary on which the probability of the value of the hypothesis function is 0.5, which means that the sample it is in a sort of the class of the sample lying on this line is indeterminate. You cannot assign it to either class 1 or class 2. So that's why it is called as a decision boundary. Okay, any questions here? Some quiz is coming up.
So I had a doubt.
Yeah.
So based on this, we have to choose a model parameters which does not satisfy this equation, right? Theta transpose x equal to 0.
No, model parameter we are yet to talk about. So how to obtain the best values of model parameter is the next topic. So that has nothing to. Okay, what you are asking is how do you decide the model parameters? Is that your question?
Yes, sir. So that, like, if 0.5 comes, it's like some problem is coming, right? Whether to choose this one or that one.
No. Means the theta 0, theta 1 are not decided so as to make theta transpose x equal to 0. So that is not the way the thetas are determined. The thetas are determined in order to minimize the cost function, just like regression or any machine learning problem. You will always have hypothesis function and a cost function. And the model parameters will be determined by minimizing the cost function. So that is our next discussion topics, how to determine the best values of theta. theta vector.
Okay, so if we get 0.5, what we will do then?
Okay, so that as a programmer you will have to decide. So means in the program you will have to write greater than or equal to zero point 0.5, it belongs to class 1. One programmer may like that, another may like less than or equal to zero point 0.5 is belonging to class 0.
Okay, sir.
Okay, so in the real life problem, you may get very rare coincidence that your hypothesis function happens to be exactly 0.50000. So it will be in terms of numerical errors, it will be either here or there. So it may come, that problem may arise. So your code should have provision for that. So obviously you can make it by including greater than or equal to in one of the sides.
Okay, sir. Got it.
Yeah. Okay. So next there is some quiz. So, so in a logistic function, the hypothesis function, those who don't remember, is 1 plus a to power minus z. So this is the hypothesis function. Okay, so responses are slow in this case. So okay, so let's look at the answers. Okay, so I'm getting answer 4 also. Okay, so option 3 is the correct one. So neither this is correct nor this is correct. So the correct answer is on the decision boundary, the value of hypothesis function is equal to 0.5. So that is what we have seen previously. Okay. Okay, so now we will discuss what we talked uh, in terms of answer to Prasad's questions. How do you determine these theta's values? So for that purpose, we have to use we have to define the cost function, and we have to minimize the cost function or the error function so that we get the correct values, the values of theta. So the cost function for the classification problem, it can, let's first see what cost function we used for linear regression. So j of theta, we defined there as 1 by 2m sigma I equal to 1 to m, that is summation over number of samples. The value of hypothesis function, so it's theta x, the feature vector for ith sample, minus the label value of that particular sample, the whole square. So this is the function we use for the linear regression. Now the same function one may think of, because that is the most simple function, so one may think of using the same function in logistic regression as well. But remember that in logistic regression, the function hypothesis function is already a nonlinear function. So in linear regression, this is a linear function. So, this addition of this gives a function which is parabolic in terms of theta. Whereas in logistic regression, we already having a function which is of a complex type, so it is already non-linear. So if you do this particular operation and you plot the j theta versus any of the theta, theta 1, theta 2, or theta 0, you will find that the cost function is not the parabolic the way we get in linear regression, but it is of this type which has gotten multiple minima. So if you use this function, you will get multiple minima type of situation with the hypothesis function as logistic function. So to reach to the global minima, which is our requirement. So at this point, that all theta values will be the optimum, so that the errors or the cost is the minimum. So to find out this using the regular gradient descent method is computationally intensive. Means you have to modify that method in order to reach there or escape the local minimas. So if you start here, the gradient descent will gravitate towards the local minima and it will not move from there. So in order to reach this global minima, you require much more computational efforts. More computational efforts. So as a result of which, we don't use the least square cost function for this logistic regression. We use an interesting function, which is, let's see that particular form of function. Okay, so having seen that we cannot use the least square function or the square sum function for as a cost function. The cost function for logistic regression is defined as follows. So the cost function for the logistic regression is defined as, so the j theta would be 1 by m sigma I equal to 1 to m. I'll just call it a cost function, which is function of x and yi. So this cost in terms of the hypothesis function for a particular sample whose feature vector is xi and label value is yi is defined as follows. So it is log of minus log of h theta xi if yi equal to 1, and this is equal to minus log of 1 minus h theta xi if yi equal to 0. So to look with it looks a bit complicated, but let's understand what it is doing. So this is not a continuous function. It is the function depends on the value of label. So for every sample, the label value will be different, and depending on the value of the label, the function takes different forms. So let's see the first form. So that is when yi equal to 1. For a particular sample, the value of the label is equal to 1. So our prediction should also be 1. So in which case, that is, if we are predicting 1, then your cost should be minimum. And if you are predicting 0, then your cost should be maximum. So that is what this cost function does without introducing the multiple minima. So what I'm plotting here is the value of h theta x versus, so that is this part versus the cost function. So cost function I'm plotting here. So note that here we want to predict y equal to 1. So tell me the value of this cost function when the h theta x is equal to 1. So h theta x1 can take any value between 0 to 1. So what we want to predict is h theta x equal to 1, in that case, the cost should be minimum. So let's see whether this function does that. So what is the value of this cost function when h theta x equal to 1?
Zero.
So it will be 0. So it is log of 1. So that is equal to 0. So the point would lie here. And what happens when the function tends towards 0? So when h theta x tends towards 0, what is the value of the cost function? So this term is tending to 0. What is minus log of 0? Or log of 0, what is the value of log of 0?
Minus infinity.
Minus infinity. So minus log of 0 would be equal to plus infinity. So this particular function, it takes the form which is of this type. So the cost starts reducing and it becomes 0 when h theta becomes 1. And as h theta tends towards 0, the cost function becomes infinite. So that is what we want, because we want to predict y equal to 1. So the cost function behaves in the manner in which we want. And the same thing you will see in the second form of the function. So here we are having h theta of x, and here is the cost, the second form. So that is this form we are looking here. So here we are trying to predict y equal to 0, means the label value is 0. So when our h theta is equal to 0, so at that time, you will find it will be minus log of 0. So the cost function would be 0 at this point. And when h theta uh, moves towards 1, which is what we don't want, you find that this becomes minus log of 0. So it again becomes infinite. So in this way, this particular cost function, it gives us the local minima. So local minima is 0, and it behaves in a fashion which is what we require. So this is the form of the cost function that is used in logistic regression, which eliminates the problem of multiple minima, which will occur if you use square sum function. So the representation of this function in this form is possible. Means you can writing code, it is possible, but there is a clever trick by which you can write this two form into a single function. So that is known as the compact form of cost function. So the same cost function can be written in the following form. So we can write cost h theta xi yi as follows. So it is minus yi log of h theta xi minus 1 minus y. Just take this thing down so that I can write fully. Minus 1 minus yi log of 1 minus h theta xi. So what this function, so this is a single function which simulates the two cost functions that we just now saw. So see when yi equal to, so whenever yi equal to 1, so this term would remain and the second term would vanish because 1 minus y will get vanished. And when yi equal to 0, the first term will vanish and the second term would remain. So in this clever way, we can have our cost function in terms of only single function, which is defined in terms of the values which are given there. So in totality, the j theta or the cost function for logistic regression. So this is for a single sample, cost value for a single sample. For the entire model, you have to minimize the cost over all the samples. So it is summation. So the j theta for logistic regression is defined as follows. So it is m summation over all the samples. So I equal to 1 to m. And in the bracket, you are having yi, the same function what I have written there. So it is log of h theta xi plus 1 minus yi times log of 1 minus h theta xi. So you sum up the cost over all the samples, and that is your uh, cost function, which is used for the logistic regression. So using this function, if you apply gradient descent, if you implement gradient descent onto this, so I will just skip this quiz because we are short of time. So if you implement the gradient descent for this particular problem, so gradient descent is we get theta j nu as theta j minus alpha times delta j theta. So j theta is what we defined in the previous slide, divided by delta theta j. So if you do the differentiation of the above function and simplify, the derivation I'm not covering here. Interestingly, you get the same function as we get for linear regression. So that is something. So don't have to remember anything new in this particular case. We get exact same form of the function. Those are curious can look into the derivation of this, or you can try yourself to derive this particular thing. So this particular form, the log terms do not appear. So xji. So theta j nu is given by this particular equation. So the derivation I'm not covering. So to implement the gradient descent by which is the basic principle is given in the above rule, you will be using, if you do the differentiation of the cost function which we defined just before and simplify, then you will get this particular form which is exactly same as that we obtained for the linear regression. So that is what we understand. Okay, so this quiz also I'm skipping. Okay, so at the beginning of the class, I said that this uh, logistic regression, which is essentially a binary classification algorithm, can be used to classify multiple classification problem as well. So multi-class classification problem as shown here. So there are some triangles, squares, and dots which are shown here. And you want to classify them using the binary classifier. So how to handle the multi-class classification? So this particular case using binary classifier is the question. So I just want you to think for a minute and give me the answer. So binary classifier, given a sample, it can classify into class 1 and class 2. But here we are having class 1, class 2 and class 3. So label values are 0, 1 and 2. So how can you think of some way in which the binary classifier can be used to do this particular thing?
So if we multiply it by 2, can we get it?
Multiply what by 2?
The hypothesis function.
The hypothesis function is 1 plus a2 or theta transpose x minus. So if you multiply it by 2, you will get the values between 0 and 2.
Yes, sir.
Okay, you mean to say that then you have some partitioning where from where to where it is 0, from where to where it is 1, and from where to where it is 2.
Yes, sir.
Is that what you are saying?
Yes, sir.
Okay, so that means I have not come across. I means it's an interesting proposition, and means I did not come across in the textbook. But yes, as my first glimpse, it can be used in that sense. Okay, so thanks, Prasad. So that is something interesting. Means I will think over and just let you know later on. Okay, anybody has any other idea?
Possibly have multiple binary classification. So, uh, like
Yeah.
binary classification has a probability of predicting whether it would be 0 or 1. So, if we run it for all cases, then we would get a probability that how well it how how actually well it is to a particular class, and then we could use those rules.
Yeah, that's right, Tathat. So that is what is the textbook or the most popular algorithm is for doing is what Nathan explained. That use multiple binary classifiers. So in multiple binary classifiers, what you are doing. So that method is called as all versus one method. Is it okay? It is called one versus all. So it is again meaning the same, but let me abide with the same title. So one versus all is the name of the algorithm. What just now Nathan said is you use multiple classifiers. So in okay, so what you do is you define h1 h1 theta x as the one classifier function which predicts the probability of sample being y being 0. So this gives probability of y equal to 0. Second classifier function which predicts the probability of y equal to 1, and h3 theta x which predicts probability of this being 2. So in the first hypothesis function, you will be considering, so let's say this is y equal to 0. So you will be considering a decision boundary. Okay, it will be, let's keep it linear. So some decision boundary. So this hypothesis function classifies between 0 and other samples. The second hypothesis function, so let's call this as y equal to 1. So it classifies between 1 and the remaining samples. And there is a third classifier H3, which classifies between y equal to 2 and the remaining samples. So you each of these means you have to make as many number of hypothesis functions as there are number of labels, and each of these hypothesis function will give, for example, the first gives us the value as 0.2. So you are trying to predict for this particular sample what is the whether it belongs to class 1, class 2 or class 3. So you, for this particular sample you get probability using first hypothesis function as 0.2, second you get let's say 0.6, and third you get 0.1. So higher of this, so this is the second hypothesis function predicts that this particular sample has 60% probability of being y equal to 1. The first one predicts that that sample has got probability of 20% of being y equal to 0, and this is 10% probability. So the highest probability wins, and you conclude that this particular sample belongs to the y equal to 1 category. So that is how the multi-class classification using one versus all method is adopted. Okay, so already we have crossed by 5 minutes. So let's stop here for today. So if you have any question, just post them